Hello viewers, once again I take the privilege to welcome you all to this fantastic webinar. This is Mohammad Farooq Hussain and it is good evening for all Bangladeshis, and for some people who are in different areas it might be good morning and maybe even good afternoon for some places. Anyway, this webinar is conducted by Jamal Nuzrul Islam Astronomy Club, JUST, and I am acting as an advisor of this club. Since the establishment, we are trying to develop and enhance the concepts of science throughout the individuals who have a desire to introduce with the unknown and mysterious realm of Earth and space. Well, there is a famous quote of Thomas Hobbes about curiosity. He said, "Curiosity is the lust of the mind." I believe that curious minds always want to know. Like, if I ask you, are you alone in this universe? Do you have any answers in your hand? I guess you are confused. Okay, forget it. Another question for you. Is there any existence of life beyond Earth? You are confused again, right? Okay, don't be confused. You will get the crystal clear and amusing explanations of these queries in this webinar, because we are going to talk about this in this webinar. That's why the title of today's webinar is "Are We Alone? NASA Technologies to Find Life Beyond Earth and Answers to Other Science Questions." This is the topic of our today's webinar, and I am sharing the topic of today's webinar. Yes. Okay, here you go. So this is the topic of today's webinar. Okay, so thank you. Our honorable guest is here to give you the answers of your queries. Okay, so just stay with us and enjoy this wonderful webinar. Yes, for this time, we are really delighted to get Gautam Chattopadhyay as the speaker of this session. Well, Gautam Chattopadhyay, thank you very much for accepting our invitation. We really appreciate your cooperation. Okay, Gautam Chattopadhyay is already joined with us. I hope I am audible to you, right? Yeah, okay, Gautam Chattopadhyay, can you hear me?
Yes, I can.
Okay, so please say hello to the viewers.
Hello everyone. I am really glad that I could be here and talking to you. And so idea of that is I will pose some questions, not that we have all the answers, but we collectively, if we are put our head together, we are trying to find answer to these fundamental questions, and that is the idea of this talk.
Okay, thank you very much. And I think you are now staying in US at this moment, right?
That's correct. It's actually 8 a.m. in California. I'm in Pasadena, California, near Los Angeles.
So what is the COVID-19 situation right now in US? Please.
Actually, it has improved significantly. And across the nation, about close to 50% of the people already got first dose of vaccine, and about 25% people are fully vaccinated, and number of cases have stabilized, but still high in the about 60,000 per day. But it's actually under control in a way. But people have to still be very, very careful, mask, and not social, not social gathering and social distancing. That is very important.
Okay, thank you, and we also hope that everything will be fine in a very short time. Okay, so great, Gautam. I will come back to you in a while. So by this time, I want to share a little bit information about Gautam Chattopadhyay. Okay, Gautam Chattopadhyay has a glorious career. Let me share them with you. First of all, he is a man of NASA. Wow, I'm sure all of you know about NASA. Okay, undoubtedly, NASA is the most popular research station in this world. And Gautam Chattopadhyay is a senior scientist of NASA. He is a visiting associate with the Division of Physics, Mathematics, and Astronomy at California Institute of Technology, USA. He was the design engineer of Tata Institute of Fundamental Research. He has authored or co-authored more than 350 publications in international journals and conferences and holds more than 20 patents. That's really impressive. Okay, let's talk about the educational background of Gautam. And he received his PhD degree in electrical engineering from California Institute of Technology, USA in 2000. Now, his research interest. Okay, his research interest include microwave, millimeter wave, and terahertz heterodyne and direct detector receivers and instruments, and high frequency radars, okay, terahertz sources and application of nanotechnology at terahertz frequencies. Okay, there are various selected awards of Gautam Chattopadhyay, such as he was the fellow of Institute of Electrical and Electronics Engineers, that is IEEE in 2011. He was also the fellow of Institute of Electronics and Telecommunication Engineers, IETE, in 2014. He received several awards like the IET Professor S.N. Mitra Memorial Award, IEEE Distinguished Microwave Lecturer Award, JPL Mariner Award. He also got NASA Group Achievement Award in several times in 2014, 2011, 2009, 2007, and 2005. Okay, he has 500 plus connections, including many famous personalities such as Bill Gates. And this is really amazing. Okay, and his Google Scholar citation is also very high, around 10,000. And he is an elected ADCOM member of the IEEE MTT Society and is the chair of the Meetings and Symposia Committee. Well, you can ask any questions regarding this webinar by commenting. We have a questions and answers section at the end of this webinar. Okay, there was a lot of talk. Now it's time for Gautam Chattopadhyay. So Gautam, please start your discussion.
Thank you very much. Farooq, I want to thank all of you who have joined in and the Astronomy Club for organizing this event. I really like to talk to young people who are young researchers, young professionals who are, we have a lot of questions, as I mentioned. However, we do not always have all the answers. So today's idea is that I will try to actually pose some of these questions and we'll tell you where we are in terms of answering them. And then also we'll show some of these, technologies that we are developing at NASA to answer, some of these. And so I will present my slides about, 45 minutes, and then I'll leave it a lot of time for question and answers, because that's why I'm sure that we always learn more when we have some discussions. So we'll try that. Let me try to share my screen and we'll go from there. So share screen. Okay, I screen sharing 2 monitors. Okay. Share screen. To share, let me see. I want to show, let's see. Yes. So Can you see my screen now?
Yeah, it is visible to us. Okay.
Okay. So, all right. So, the topic of today's discussions is, are we alone? NASA technologies to find life beyond Earth are answers to other science questions. And I chose this, this background for a particular reason, because we are always curious. And what you see here is a small girl is, kind of going to Mars and trying to find out if there is life. So it's kind of an astronaut on a Mars, and hopefully that will be a woman. So that's the idea of this slide. So let's talk. So I first want to acknowledge my group members. We have a small group of people who develop technologies for answering some of these questions. So if you look at the faces of these people, you'll realize that they come from all over the world. So one of the reasons for the success behind NASA is we have the diversity. We have the diversity of thoughts. We have the diversity of the people. And that is very important. So I always tell students that when you talk to your friends, do not just talk to people who are working only in your area. So try to talk to people who are also working in different areas, because sometimes you get feedback that is much more useful when you are talking to other people. So a little bit about NASA and JPL. NASA, many of you know that our headquarters is Washington, DC, and that is in the East Coast, and then we have NASA labs all across the country, and we are at the other side on the West Coast in California, Jet Propulsion Laboratory. This is one of the largest NASA labs, and we do robotic missions, mission to Mars that is going on. I'll talk a little bit about that, of course. So let's start. This is the Big Bang Theory. The Big Bang, this is not the Big Bang Theory that you watch on TV. This is the real Big Bang Theory. So we believe that our universe started with a Big Bang, with an explosion about 13.85 billion years ago. And if we want to understand what happened, how we all came about, and in electromagnetics, that's the electromagnetic radiation, then we can go back all the way up to about 400,000 years. That's about 380,000 years after the Big Bang, when the first radiation of this universe came out. And that is called the cosmic microwave background radiation. Because beyond that, before that, not that there was no radiation, but nothing could escape this hot plasma that was created because of Big Bang. And so we can go back all the way up to that time. And if just for a little bit of information, that cosmic microwave background signature, the signal first was detected by two physicists, Penzias and Wilson, in 1964, and they got Nobel Prize for that. So there's a very interesting story about that. So so we have been about the search of life. I want to talk a little bit about Mars as well, because Mars is our closest neighbor, and we go there from time to time. And last 2 decades, we have been sending rovers, landers and rovers on Mars, who land there, go around and trying to do experiments. You can see that in 1996 we had Pathfinder, and then Spirit and Opportunity 2003, then Curiosity landed in 2011, and that recently, earlier this year, we landed Mars rover Perseverance. And Perseverance has started doing exploration there, and we are getting some amazing data already. I'll talk more about that, and also you must be reading about the Ingenuity helicopter that has, already took 2 flights. So there are a lot of instruments on Perseverance, and one more right now. What you are seeing is the cameras, that Mastcam Z and Navcam, all those cameras are actually taking pictures and sending back. And also there are many instruments. One of them is called MOXIE, and MOXIE is creating oxygen on the Martian surface from carbon dioxide. And just most recently, yesterday, we got the news that it produced a good amount of oxygen for the first time. That is a huge success. And this is the picture of the Perseverance rover when in our lab here at JPL, it was just getting packed up to send to Florida for launch. So this was just, just before its launch, that when you packed it and send it. So landing on Mars is extremely challenging, and more so when we are using a huge, big, rover. This is, weighs a lot. So what happens is, because Mars has a very thin atmosphere, 1% of planet Earth, so it doesn't have enough friction to slow it down. When we are entering at the atmosphere of Mars, we are traveling, just before that, we are traveling at about 77,000 kilometers per hour. That is a huge speed. To slow it down, on Earth, what happens, our atmosphere, it slows down quite a lot, but in Mars, we cannot do that. So we'll have to be very, very, precise in how we enter the Martian atmosphere. What we do, we come at an angle about 11 to 12 degrees so that we have enough path that will provide us this braking effect on this spacecraft. And then we release a parachute, you can see here. And after the parachute is deployed, then what happens, we turn on some of these thrusters that slows us down. And then towards the end, we have something called a sky crane that releases our rover and goes all the way down. So that is that's how we land on Mars. So this time Perseverance rover we have chosen the location very carefully. It has landed near something called the Zero crater. So this is artistic impression that we believe there is a big crater and there's kind of a lake at the crater, and there's a lot of water. However, if you go there now, this is dry. If you on the left panel, you can see it's actually dry. We landed very close to that, and the Perseverance rover will take this path to go around and do experiments. And also there is helicopter that I talked to you about. So this is the pictures when the Perseverance rover was landing on Mars. You can see here, this picture on the left, it was taken by the module which had this crane, which was lowering it down. There was a camera mounted there. This is the actual footage when the crane was lowering the Perseverance rover towards the ground. And this on the right side, what you see that we have two orbiter that is going on Mars, going around Mars. One of them is called MRO, a Mars Reconnaissance Orbiter, and another is called MAVEN. So they also took a lot of pictures when the Perseverance rover was going down. You can see here that when the parachute was deployed on the right top panel, and then you can see all the small, small images of different parts after it landed, where where the parachute went, when the descent stage went. Here is at the bottom, you can see the rover itself. So these are real pictures. So we are on the surface of Mars at this time. And this is the picture, panoramic picture that Perseverance rover sent. This is beautiful. If you look at this, you will realize that how closely this resembles our own planet Earth. So that is the intrigue, and that's why we actually are very much interested. If you look at the terrain here that Perseverance rover has sent, and Curiosity also had sent similar pictures before, you can see we get this kind of terrain only when there is flowing water on any surface. But when you go to Mars now, we don't see flowing water. So the question is, what happened to that water? So what can we do? Can it happen to our own planets one day? So currently the distance between Mars and Earth is about 260 million kilometers. That is 26 crore kilometers. That is a huge distance. So, but to reach Mars, we had to actually we had to travel about 400 million kilometers, because we have to launch at a time when Mars is not there, when we are going to reach, because both Mars and Earth is rotating, right? So we'll have to have precise calculations to make sure that we arrive at the orbit of Mars little bit ahead of time of Mars, so that Mars will catch up from behind, and then we are going to enter there. So all this stuff needs a lot of precise calculations, and but we are getting very good at it nowadays, that we can actually do this, because 70% of the last 6 successive missions landing on Mars by NASA has been successful. So that is, we are getting better, but it's always very, very challenging. So again, I was showing this. This is again another picture that was taken by Curiosity. You can see here this terrain. We do not get this kind of terrain when there is no flowing water, which means that at some point of Mars, there is flowing water. But if you go there today, there is no flowing water. So this is very intriguing, and we are trying to understand what happened. So one of the questions that people might ask, that why do we go back to Mars from time and again? Why not somewhere else? Why Mars? The reason is that if you look at Mars, Mars resembles Earth in many ways, especially in its early history. The question we have is, was Mars ever a habitable planet? Was there life on Mars at any point of time? Or is there life on Mars today? So this is the question. This prime mission, the purpose of this perseverance is to answer this question. And we believe the Jezero crater where you have landed, it is an ideal place, because if there was a lake at one point of time, what is underneath? What is currently out there? Is there any signature that we can find? So this is the idea of that. So if we are trying to answer this question about life outside our planet Earth, I am asked this question, very often. So if you ask me today that what do I think? Are we alone? Is there life anywhere else? Just to be sure, I want to tell you that we have not found any sign of any life anywhere outside our planet Earth yet. So whatever you read on internet about all these aliens, that is not true. If you find any aliens, let us know. We'll be very happy, but we have not found any. But if you ask me this question, is there possibility of life anywhere else? My answer to that will be highly, highly probable. Why do I say that? You can do a back of the envelope calculations. You know that our sun is a star, and it is in our galaxy, Milky Way galaxy. And we have about 100 billion stars, order of magnitude, in our own galaxy. And it turns out there are about 100 billion galaxies in our universe. All of you know how to do math. If you do your math, you will know that there are about 10 to the power 22 to 10 to the power 23 stars in our universe. And we are finding, like our planet, our sun has how many planets? 8. So we are finding that many of these stars, of these hundreds and trillions of stars out there, many of them have many, many planets. Not only one, many planets going around them. So the question is, what is the probability that we find at least one such planet where conditions are such that life can exist? So that has to be finite, that probability, right? So that's why we are kind of confident that maybe life has developed somewhere else. We don't know what form of life, we have no idea, but there is a possibility. And that's what we are trying to actually find out. And that is the quest. That is the biggest quest of human being, to find out that, are we really that unique? Are we really alone in this universe? And that's why that quest is ongoing. So I talked about all these planets, right? They're called exoplanets. So we have been finding, so far we have found more than 4,000 exoplanets. That is planets not in around our own sun, so around other suns. If you can see that we are finding all kinds of planets. Some of them are big, gas giants like Jupiter, and some of them are like our planet Earth. So when we are looking for a planet to find life, what we call the planets in the habitable zone. What we mean by habitable zone is planets where the temperature is such, the conditions are such so that water can exist in the liquid form on the surface. So they are called the habitable zone planets. They have to be rocky planet. We know that life cannot be sustained, at least the kind of life that we know, on a gaseous giant like Jupiter. So it has to be a rocky planet. So we are looking for rocky planets. Also, we are looking for the planets where, the conditions are such that water can exist. Why why are you looking for water-based? Because, kind of life that we know, they are hydrocarbon based. They need water, they need oxygen to live. So that's why you are looking for that kind. So a lot of people ask me that, well, maybe there will be life other form, not like our kind. Why aren't we searching for them? My question is, how do you search for them? If you don't know what to look for, how do you look for them? So that's why we are searching our kind of life. Many of you have read about Rabindranath Tagore. So Rabindranath Tagore has a beautiful song. And one of the line of that is, Janar majhe ajanare korechi sandhan, that we are searching for the unknown through what we know, right? So that's why here we are looking for life, in outside our planet Earth, through the knowledge that we have. And our knowledge of life is what we know today. And that's why we are looking for. It is possible that we can stumble upon some other form of life, but but we cannot actively search for that because we have no idea what to look for. And the question is that, as I mentioned, there are trillions and trillions of stars out there. Then how come we have only found 4,000 planets? Why not more? The reason is we have started looking only very recently. So far, we have looked only this region of our own galaxy, the Milky Way galaxy. So as I said, there are 100 billion galaxies like this, and we have not even looked at our own galaxies in all the stars. So the reason is we do not have the technology to go beyond this and really precisely look at those planets. So it's very, very difficult. So we'll have to develop new technologies. And that's why I am looking at you, so that you all will be able to help us develop new technologies so that we can actually look beyond our own galaxy to find more and more exoplanets. So how do we actually find an exoplanet? How do we find when you are doing what do you do to look for an exoplanet? This is a very simple way to look at one of the technique that we use called transit time detection method. So what happens is, if the planet is going around the star at the way on the left of the top left screen, we won't be able to see, because that is in our line of sight. We won't be able to detect that planet. However, if the planet in our line of sight is going around the way on the right top side, then we'll be able to detect. What we do is that we actually isolate that particular star. So light that is coming from the star, we isolate, and we try to measure the total amount of light that is coming from that star. And then if you see the brightness of this star, as the planet goes in front of that star, the amount of light that is coming will dip ever slightly. And by detecting that, we'll be able to tell that there is a planet. And then we actually can know a lot about looking at the time, transit time, how much time it has gone, about how big that planet is and how far it is from the star. And then we can do some calculations and find out, is it a rocky planet, is it gaseous, what is the density of that planet. So we can also find out about the temperature, what could be the temperature, because we know how bright that star is. So there is a lot of things you can do once you make this kind of measurements and know about that particular planet. So that's what we do. This is one of the methods. Another method that we use, it's called Doppler effect. So what happens is that you all know Doppler effect, that frequency changes when something is moving away from us or something moving towards us. So in this case, if we actually lock at a frequency, and as the planet goes around that star, the frequency changes ever slightly. And by detecting the change of frequency, we'll be able to tell, because of the Doppler, that that is a planet. So these are all different techniques that we use to detect the stars. So let's talk about, now we are finding more and more of these, planets, and with the search is on, and we have already found quite a few of these planets which are in the habitable zone, with Goldilocks zone, and they have their rocky planets. There could be, the temperature is also kind of very, very, conducive for life. So we are now looking for more evidence, so either in atmosphere there. So for that, we need much better technology, much better instruments to do that. So let's search for water. I said that the kind of life, hydrocarbon-based life that you are looking for, it needs water, right? So is there water out there in the universe? The answer is yes. And we actually built an instrument called Herschel Hi-Fi. I was part of the team. We built that instrument, and that detected water come in, sun-like stars. And we found that the water is not only water there, it's coming out at a very high speed, 200,000 kilometers per hour. Water is coming out from these stars. And if you know that if you fire a bullet from a AK-47 rifle, not that you should do that, but I'm just saying the speed is about 2,500 kilometers per hour. So these water molecules are coming out at 80 times faster than these bullets. Then what happens is, if something traveling that fast, it generates a lot of heat, right, and try to destroy itself. However, using this kind of instrument, we are finding that conditions are such that it finds a way to recombine and generate huge amount of water. How much? About 100 billion times the total amount of water in the Amazon River is being formed every second in these stars, which means this universe is flooded in water. So there is a lot of water out there. So the question is, if there is water, is there life? So that is the question we are trying to answer. So another very interesting thing that you will know, that actually when our Earth was formed, there's no water. And scientists believe that comets brought water to Earth. If I tell you that, I'm going to tell, okay, comets brought water to Earth. That case, you are going to ask me, I don't believe you. What is the proof? That is a very good question, because as a scientist, as an engineer, we'll have to always ask this question. And if you don't ask this question, you are not going to get these answers. So what we do to actually determine this is a very simple method. It turns out that water has different colors, in the sense there are different kinds of water out there. The most common, the one that we drink every day, is H216O, that the 16th oxygen isotope. That is the most stable water, most abundant form of water. But the other kinds of water, H217O, H218O, HDO, one hydrogen, one deuterium, one oxygen. And you all know about heavy water as well, like D2O as well. So it turns out, if you take the ratio of different kinds of water, the abundance of different kinds of water, as well as D over H, how much deuterium and how much hydrogen, this ratio, if you take, it turns out that the Earth's water, these ratios matches very closely with some comets. If the ratios are same, the source has to be the same. And we have made about 10 to 12 such measurements, but not enough. So currently, actually, I am building an instrument to go on a very shoe-sized satellite to go to comet and make this kind of measurements at a very easy way. So I'll show some of this stuff, that what I'm doing to do this. But it will be very intriguing, because that answer, we have not settled that question yet, that did really comets brought to Earth? It's looking that way, but we don't know yet 100%. So when I talk about we are looking for exoplanets, but we cannot really go there yet to find all these exoplanets, is there in life? Because one of the places where we found a planet which is in the habitable zone is 4 light years away. And if you want to go there with current technology, it will take about 40 million years to go there. which means we are not going to go there in our own lifetime, right? So what do? We are now, question is, okay, there could be life outside. But is there possibility of life in our own solar system? So this is the question that we are looking into, and there is huge possibility. One of the places is Enceladus. Enceladus is actually moon of Saturn. It is a very cold planet, and it turns out that it's kind of icy. However, through this hi-fi Herschel instrument, we found that water is gushing out from Enceladus. If you actually zoom on that, you can see what is coming out. These are all water, which means even if it is very cold, but there is some mantle, there is source of heat that is making this water liquid form. So what else is coming out from in this water? Is there life? If there is water, if there is source of heat, that possibility of life. So we are actually looking into that, and maybe NASA is planning in future, maybe there will be a mission to Enceladus to actually find out what else is going on. So that will be really interesting. Another place that there could be life, we believe, is Europa. Europa is a moon of Jupiter, and it is again a very cold planet. And it turns out, we have actually, through experiments, we found that Europa, of course, this is very cold and they have ice, ice everywhere. But under the ice shell, there is a liquid water ocean. That's what we believe. And if there is a water ocean, which means there has to be a source of heat. And the question is that if there is water, there is a source of heat, is there life in the water ocean of Europa? That is a very intriguing question, and we are trying to answer that. And if how do you actually do that? How do you do that experiment? It takes 7 years to go to Europa. But it turns out that all this ice that we have on the surface of Europa, that is thick about 15 to 100 kilometers. But there are a lot of cracks into that, and this water, this material, seep all the way to the top. But whenever it reaches to the top, it freezes, right? And then but Europa is very close to Jupiter, and Jupiter has very high magnetic field. So what the magnetic field does, the radiation does, is sputters all the material from the surface in the atmosphere. So we are building instruments to trying to find out what is those material that is coming in the atmosphere. Is there organic materials? So that's why we are building these instruments to answer this. If there is organic material, there is possibility of life. Organics does not necessarily mean life, but there is possibility. And then there could be life on Venus as well. Recently, we actually found the evidence that maybe Venus atmosphere, Venus is an extremely hot planet. We all know that, right? The surface temperature is about 700 degrees Celsius. However, we are finding that in the upper atmosphere, if you go 50, 60 kilometers in the atmosphere, the temperature is very, right in about 20 degrees centigrade, 25 degrees centigrade. And there was a detection of phosphine in the atmosphere of Venus, and that has created a lot of buzz that some scientists believe that amount of phosphine can come only from a biotic process. That means some kind of life form can generate. We are trying to actually look into that. There will be future mission to go to Venus to answer this question. You can see on the right, there's an article I wrote in one of the newspapers in Calcutta about this. So those are the science questions. I actually spent a little bit of time about technology, what kind of technology that we are developing. So if we are trying to, go to these places, go to Enceladus, go to Europa and other places, one of the key technology that you need to develop is that you have to miniaturize everything, because mass and power is the main driving, challenge that we have. So we have been very good historically to miniaturize. You can see this is the first IC that was built in 1960, only had 3 to 4 transistors. And then in 1969, we had this Intel to develop the SRAM chip. It has about 2,000 transistors, but nowadays we are building chip that has billions of transistors, billions and billions of transistors. And we are producing about 10 to the 19 transistors per year. That is, 1,000 transistors per every ant on planet Earth. So most of them work. So we are getting better at that. However, just making a chip is not going to do it. So what we'll have to do is we'll have to put the instrument together. And what we are looking for nowadays is building instruments on a satellite in a shoebox size. It's called CubeSat. And students can work on it. And the best part is students across the globe, they are actually started building this kind of small satellites called CubeSats. Their size is how much? They go in terms of unit of U. 1 U stands for a cube of 10 centimeter by 10 centimeter by 10 centimeter. So it's a very small satellite, but everything has to work in that. So that is the challenge. And we have been building a lot of, sending quite a few CubeSats, and many of them are in the planning as well. And recently, the first CubeSat that you have sent to Mars is called Marco. So what happened is, when the spacecraft goes in the atmosphere of Mars, we do not have direct communication link to Earth. So we work in the dark. So we call it 7 minutes of terror. So to avoid that, for inside spacecraft, we had released 2 CubeSat to actually communicate, and it worked very well. That was the first CubeSat that we used. And another one that we are actually, we have developed called RainCube. This is on a radar instrument. Sorry, I'll go back. So this is a radar instrument on a, again, shoebox size satellite. You can see here, you are deploying an antenna that is 50 centimeter in diameter in a but it has to be stored in a very small volume. So how do you do that? There are a lot of challenges to do this. So we overcame that through innovative ideas. This is the antenna that we developed. This is 50 centimeter antenna, but it has to be stored in a 10 centimeter cylinder volume. So that was the challenge. We actually solved it. And I'll show you a video how the antenna deploys. You can see here, sorry, again. So I'll play this, hopefully it will play. You can see here, we just release a small spring, and then the antenna deploys. You can see that it's deploying. It's like an umbrella. And then there will be another part that is the subreflector that also gets deployed, and then the antenna works perfectly. So this is the way we'll have to see. When we are developing instruments, when you're working for NASA, we are always faced with different challenges, and we'll have to overcome through innovation. And innovation happens when people, all of us, put our head together and we are facing a difficult problem to solve. So that's what we did. And also we built a lot of other kinds of antennas that can go on the sidewall of a CubeSat. This is an antenna I call Fakir's bed antenna. These metallic pins that is sticking out, and this is very thin. The thickness of this antenna is thickness of your hair. So you can actually put it on the sidewall, metallic sidewall of the spacecraft itself that behaves as an antenna. And so I was telling you that I am building an instrument that can go to the comets. What I call the instrument is WhatsApp, not WhatsApp, is WhatsApp. So water hunting advanced terahertz spectrometer on ultra small platform, because we are trying to answer this question, what's up with water? So this is again on a small CubeSat in a shoebox size satellite. It's extremely challenging, but we made amazing progress. If you are interested, I can go into details later on. Because it works on, as I was saying, different kinds of water. It will detect HDO, H217O, H218O, and H216O. And it's a very small instrument. It weighs only 2 kilograms and draws less than 5 watt of power. And we have made a lot of innovation here to solve a lot of challenges that we face. And this is some more of these details. And you can see, sorry, this one is, so what we have done is here that you can see that we put everything together. It had come together very nicely, this instrument. And so that instrument has come together very well, and we will be able to launch it sometime soon. And so I have a few more minutes I'll take to talk about the Mars helicopter, because I know a lot of you are very excited about the helicopter, Ingenuity helicopter. So why we are sending a helicopter to Mars? Because, when you send a rover, the rover can go at certain places, but we thought that if we can send a helicopter, then it can take off and go around on Martian surface and send some data back. And with that, we'll be able to decide where are the interesting places, and the rover can go there. So this is some of the details of the helicopter. If the flight duration of the helicopter will be at least 2 to 3 minutes, it has about 600 meters range. So it will hover around, maximum height, it will go about 40 meters above the ground. So why it is challenging to send a helicopter to Mars? We have seen helicopter on planet Earth on a regular basis. The difficulty is that Mars has a very light atmosphere, 1% of planet Earth. So that to get enough lift, the rotor blades has to rotate really at a very high speed, about 2,500 to 2,600 RPM, revolution per minute. But on planet Earth, we need about only 400 to 600 RPM. So this helicopter has, it weighs about 1.4 kilograms. The wingspan of this blade is about 1.1 meter, and it needs about 200 watts of power. It has solar panels on the top of this helicopter. That's how it does. And it is fully autonomous. It has all cameras, gyroscopes, accelerometer. It does everything on its own. And so these are the pictures of the helicopter that is being released on Mars from the Perseverance rover. You can see here on the left panel that there was a cover that was covering Mars, this helicopter Ingenuity, and then that was first dropped, and then slowly the helicopter being released. You can see 3 different pictures, and then it was fully down on the ground. It is being lowered down on the ground, and then you can see on the track marks on the right side when the Perseverance rover moved away after dropping the helicopter on the ground. And this week, 2 flights, first flight of the helicopter was done. So first flight, the helicopter went up about 3 meter distance, at the elevation, it went up 3 meters in hover for about 40 seconds. It made a kind of rotation about 96 degrees and then came down again. That was the first flight. That was the first time after, Wright's brother did the first flight on planet Earth. That is the first flight on Mars. And then yesterday, we had the second flight. The second flight was that it went up to 5 meters distance, and then it made a tilt about 5 degrees and went ahead for 5 meters, and then came back again and landed. So both of them has been successful. That is really, amazing if you think about it, to fly something on another planet which is extremely challenging. So I will end my talk with this slide that you can see here. This is the helicopter just before it was packed on the Perseverance. So this is amazing, and we are looking forward to hear more, in coming days from Perseverance rover as well as from this helicopter. And with that, I will end and I will stop sharing my screen. So how do I stop sharing my screen? So are we back? Have I stopped sharing my screen?
Yeah, okay. This is a stop. Okay. Okay, so thank you very much for your informative and wonderful presentation. Now this is the time for the questions and answer section. We get a lot of questions from the viewers. So we can start this session, right? And,
sure. Please go ahead. If you can pick the questions and read out to me, that would be great, because for me it's difficult to see the questions and I'll leave it up to you to which questions to take.
Okay, sure. So the first question is from Anup Kumar Pal. Okay, this is the question, and Anup asked that, don't you think that this is the time to leave Earth and search for new ones? Okay.
Very interesting question, but problem is, or the challenges that we have is we do not really found any better place to live. So if you think about Mars and other planets that where you can go, they are not very, they're not livable. So the best place in the universe for us is still our planet Earth. So instead of leaving it behind, it will be better to take care of it. So we make sure that all of us do our part, and we take care of our planet Earth, so that we preserve the one or the only planet that we know so far that can where we can.
Okay, thank you very much for your answers. And then the second question is from Ben Hur, and the question of Ben Hur is, which facts are against an oscillating universe?
So, okay, again, this is a good question. With what we know so far, you have to look at the evidence. So far, the evidence that we are seeing is a ever-expanding universe, because if you look at, that Hubble constant and everything that we can measure, right? That is how they're moving away. And from the evidence-based science, if you look at, we see evidence is pointing more and more towards an expanding universe. And that has started with the Big Bang. So if someone comes up with a theory that is borne out by some experimental evidence with the oscillating universe, of course people are open to it. But so far, again, evidence suggests that it is an expanding universe.
Okay, thank you. Thank you very much. Okay, now another question from Anup Malakar, and his question is, especially, why do we need to find out lives in exoplanets?
So this is actually fundamental question for human being, that we are explorer by nature. We want to find out how things work. That's how we actually came. Not only it's actually improve our own life, current life in the process, because when we are trying to find out new things, how things work, the new science, and one of the basic questions human beings always ask themselves is that our form of life, how did it evolve? How can you be so unique that only life can evolve here, not in other places? So we always want to answer this fundamental question, and that's why we are doing. But in the process, we develop technologies that improve our life. Currently, I am sitting in California, and some of you are sitting in Bangladesh, and we can seamlessly talk through video. How did it happen? How did it come about? It came about with a lot of technologies that have been developed for space applications, space science. So in the process of doing science, we develop technologies that improve, our life, our day-to-day life. So we'll have to always keep that question in mind when we are actually trying to answer these questions.
Okay, thank you. Thank you very much. Okay, there is another one, and this is from sulfuric acid. Okay, so and he asked, is there really exist multiverse?
Multiverse, we do not know yet. We have not seen any evidence of multiverse. So if you think about evidence, but we cannot definitively say, because whenever we are answering this kind of question, there is no correct answer. Only thing we know, based on the evidence that we have seen, that we have only one universe. So if you find evidence that yes, there exists multiverse, only then we'll be able to say that. So as of now, we have not seen any evidence.
Okay. So thank you. And then another question, and this is from Shapnil Sohashini Orko, and his question is, why does the universe have to be so grand a scale of space and time?
Good question. I wish I knew that. Because the way the universe was created, that we know, at least we think we know from the Big Bang, there's a huge amount of material that existed, and then this material is spreading out. So if you actually integrate all these materials, it is huge and grand. It is, yes, we are in awe that something how so grand. Space and time, and that makes it much interesting as well, right? If we are really tiny, small universe, not this grand scale, maybe you'll be able to solve many of these, answer many of these questions much more easily.
Okay, so thank you. And then another question from the same viewer participant, and this is the question: why the universe itself can't be the most fundamental thing?
I don't know what exactly you mean by this question. Of course, universe itself is the most fundamental thing in a way, because that our universe exists is fundamental, it's real. So it's not clear to me what exactly you mean by this question.
Okay. So thank you. And now this is the question from Nasrin Afroz, and he asked, what is the relation between organic material and life?
It's a very good question. If you think about it, life is built of organic materials, right? So if when we're searching for organic materials, but organic materials does not necessarily mean life. It is a required condition, but not sufficient. But if you look at the other way, all life form has organic materials. So that's why this is important.
Okay, thank you. And then this is the questions from Imran, and he said, so far we can detect exoplanet atmospheres through transit spectroscopy. Just wondering if we would be able to somehow decipher the surfaces of exoplanets once JWST is up in space.
That is a very, very good question. That is absolutely true, because the JWST, when it's launched, this is James West Space Telescope. So when it's launched, it will James Webb. Sorry, I said West. So James Webb Space Telescope, when it's launched, it will make a big leap in this field, because it's much more powerful than the current generation of telescopes. So we'll be able to see a lot, we have to learn a lot. However, it is not going to solve all our problems, because we still won't be able to directly detect this planet. So all this detection that we are doing, there are indirect methods, right? Transit time methods and others, the indirect methods. We are not really imaging the exoplanets directly. So JWST will do some work in that direction, but again, this is not able to look far beyond our own galaxy and directly image exoplanets. But you are absolutely correct that it is going to make this first step in that direction.
Okay. Yeah, thank you. And now I'm going to pick up another question, and this is from Al Muzahid Afridi. And he said that the fact that the galaxy Andromeda comes towards the Milky Way is not in contradiction with the Big Bang.
Not really. So basically, if you look at Andromeda, and if you actually do the calculations of this, what is the speed, what is happening there. So it is not in contradiction. Andromeda is actually, it seems it is coming towards, our galaxy is from is kind of a parallax effect, and so it is not true. So far, all this evidence that we have seen is following this Big Bang model.
Okay. Thank you for your answers. And there is another question from the Al Muzahid Afridi, and His questions is, why are experts so sure that extraterrestrial life exists?
It's not about experts. It's about just doing back of the envelope calculations. So it is if you ask even non-experts and give them the facts and ask them. So you have trillions of stars, and they are that, and trillions of planets around them. So if you do the simple probabilistic calculation, and that's where it leads to, that does not necessarily mean that we will be correct, that we might land up finding no life. But if you, from your simple probabilistic calculation point of view, it makes sense to be positive and to be hopeful.
Okay, so we're also hopeful. Okay, so thank you. And there is another one, and this is from Deepa Mandal. Don't you think that there have so much possibility to be hampered by the golden record?
So what is the golden record? So do you know, Farooq?
Yeah, maybe actually, I'm not sure about golden record, because I think it will be helpful for us. If
so we can come back to that. We can ask Deepa Mandal to actually explain.
Okay, so yeah, Deepa, you can explain your question and you can give the record. Okay, so if we get the record, then I think it will be possible to give you the answer. Okay, so please, you can clarify your questions. Okay, so okay, then another one, and this is from Ali Murtuja, and his question is, what was the mechanism of creation of first organism on our planet?
So this is a good question. We actually still don't know. Still don't know. We are trying to find out how it happened. What conditions led to the development of the first organism. That we don't know. We know that it happened about 4 billion years ago. That's a lot of things have to come together, but with that thing is still on. So that's why it is very important that we spend more time trying to understand that how the first organism was created on our own planet. So there are a lot of theories out there, if you look into that, but we still that is still not a very convincing proof-based theory that will say that this is how this is the reason the first organism was created.
Okay, thank you. This is basically the golden record, I think. Okay, so this is some information about golden.
Okay.
So the Voyager golden records. This is basically two phonograph records that were included about both Voyager spacecraft launched in 1977. The records contain sounds and images connected to portray the diversity of life and culture on Earth, and are intended for any intelligent extraterrestrial life form who may find them.
Oh yes, now I know what you mean. Okay, so I was not making this connection here. So I will go back to the original question Deepa Mandal had was, don't you think that there have so much possibility to be hampered by the golden record? I don't see there is any possibility of being hampered by golden record, because what we are trying to do is through this, why we do that with our hope that one day maybe Voyager will land somewhere, will reach somewhere, and then there's some intelligent life out there. They will find it, and then when they see these, they'll know, okay, there exists another planet where maybe there is life. So it is the same way that we do, that extraterrestrial. There is some program where we send, we send SETI, Search for Extraterrestrial Intelligence. So we send some, very precise kind of signals, which follows some kind of binary code, so that cannot be generated from a non-intelligent life. So if you look at natural signals, so it is different from natural signals. So if someone detects that, which has some intelligent life detect that, they will know, if they're intelligent enough, then they will know that it is coming from a non-natural source. So that might intrigue them. That's what the SETI project is all about. So similarly, I don't see that golden record is going to hamper in in any way. It might aid, but again, that possibility of that some intelligence life is so nearby is remote.
Okay, so thank you for the clarification of the question of Deepa Mandal. And right now there is another questions, and this is from Ali Mortuja, and he said, why does our planet hold lives? Is it random selection of the nature?
Again, that actually relates to the other question. So it is a combination of a lot of things, right? So it could be a random selection of the nature, or it could be that there is some, some events. If you try to, generate life inside your lab, then you know that what can you do that? All the different ingredients come together, but still life is not generated. So some precise conditions has to come together with these inanimate objects, these atoms, then that creates life. So what is that process? Was that natural selection? We don't know. So that's why we really need to, that quest is on.
Okay. So thank you. And this is Farid Ahmed Sakib, and his question is, we know the atmosphere of Mars and Earth are not the same. So whenever it will return with sample, then do you think those will give you the same value that would have give in the red planet?
So that's what we're trying to find out. So that is, we are trying to bring one of the key mission objective of Perseverance, the first step to our sample return. Because a lot of experiment that we need to do on Mars cannot be done because we cannot really send big instruments there, right? So there is limitation of what we can send, but we have much more capabilities here in our lab. So what we are planning to do is that we are collecting samples. So Perseverance Rover will do that and keep it in small cylinders. They are size of a chalk that we write on the board. So that kind of 40 of such samples. And then in future mission, there'll be 2 more missions that will, one of the mission will go there, collect those samples, put it in a kind of basketball size container, and that will be launched in space in Mars orbit. And then another mission will go there, collect, capture that and bring it back to Earth to do experiments. So we then will know that the ingredients could be same, but maybe the texture, maybe the properties of these materials could be different. And that's what we are trying to understand, whether that environment played a role in making those rocks compared to our Earth. So that is that is one of the experiment that we'll have to do to understand.
Okay, so thank you. And Nasreen approached once again, and her question is, how will the Martian, I think this will be Martian samples be delivered to Earth? That is
I already mentioned. I just in the previous question I said that we need 3 missions to do that. The Perseverance will collect them, and the next mission will capture, collect all of these, put it in a container, and there will be a rocket there, small rocket that will launch it in Martian orbit, and it will go around on Mars. And then about 2030, 2031, there will be a mission called Mars sample capture. So that will capture that and bring it back to Mars. So that is the plan as of now.
Okay, so this is an interesting question, and this is from Farid Ahmed Sakib, and he said, think there are another civilization and they are more advanced than us. If so, they can easily destruct or destroy to experiment. So then what will be your solution?
I'm looking towards you to suggest a solution, because first of all we have to find another civilization which are close enough. Maybe there exist. We don't know, and if we find them, maybe they will find us, and then they will come and and take over. Of course, those sounds very interesting and kind of science fiction, but again. We do not even know whether another civilization exists, and so if there is more intelligent life form exists, that could be a challenge. But again, we'll have to first find them.
Okay. So we are welcoming the civilized society. Okay. So okay, right now this is an interesting. This is basically a proposal, and you talked about the collaboration, and you said that NASA basically is a place where we get a lot of people from various parts of the world. And this is a question from Polash Dhali, and he said that what is the best way for us to collaborate with you? So how we can make it possible? Okay.
So NASA has a lot of programs. So go to nasa.gov website and you'll find that actually there are a lot of internship programs. That's how the collaborations start, right? So you should apply for those, and then basically, of course, it's very selective process, and then you can come and then you can collaborate. So that is, again, if you develop some CubeSat based, let's say small satellites, some instruments, NASA actually has program to launch them. Other space agencies also, they have programs to launch them. So you should look for those, and that is the best way to collaborate through that. Go to NASA website, see all those opportunities out there, and apply for them.
Okay, so thank you, and I think this can be the last one, and this is from Nasina Pros, and her question is, why scientists set this rover name as Perseverance? Okay.
So actually, scientists did not set the name. What NASA does is a very nice thing, that they make an open competition whenever we have a mission like this, and we ask school students to come up with a name, and not only name, then they'll have to write a small essay, short essay about why they want to name this. So this name Perseverance was chosen by one of the middle school student from East Coast of the United States, and she actually wrote a very nice essay, and amongst all the names, this was selected, and it became very apt because of the COVID situation, if you think about it, because we had to persevere to be successful under all these trying conditions. So it turned out, in hindsight, it was the most perfect name for this mission.
Okay, so thank you very much. So I think that was the last question of this section, and we hope that in future NASA will give us many more new and amazing inventions. Okay, okay, so we can stop now, and thanks again to Gautam Chattopadhyay for his valuable time and cooperation. Thank you everybody for being with us, and next time see you with any other webinar. Till then, stay well. Okay,
thank you very much.
Thank you, and take care, and best wishes for you. Okay.
Thank you.
Okay. So goodbye, everybody. Bye bye.
Okay, bye.